My name is Hamid, and I'm here to present our work, Every Vote Counts, ranking-based training of federated learning to resist poisoning attacks. This is a joint work with Amir and Virat. So in real-world setting, data is dispersed over different organizations and clients, and they want to preserve their privacy restrictions. Federated learning, or FL, allows mutually untrusted clients to collaborate and train a shared model called global model without explicitly sharing their local training data. In FL, the objective is to find a common model that works well on average on all the clients and without sharing their data, meaning that we want to minimize the average loss for all of the clients. In FL, the poisoning adversary owns or controls multiple compromised clients, and the adversary poisons the global model by crafting malicious updates in these compromised clients. Now I will talk about what is the high-level intuition behind untargeted poisoning attacks. So in a general FL framework with no security mechanism, such as FedAverage, the space of possible updates that the clients can submit in each round is continuous. It means that the clients are submitting their model updates that, the weight parameters, that each weight parameter is represented using 32 64 bits float numbers. And the server aggregates all of these updates into one global model by just averaging the updates. It is easy to attack these kind of FLs because to do so, the adversary just sends malicious updates to maximize the distance between benign and malicious aggregations. So a recent line of works designed Byzantine robust aggregation rules by shrinking the space of accepted updates. Usually these robust aggregation rules, they define a safe space and they exclude the updates that they are not in the safe space. For example, if their L2 distance from other updates is larger, they will be excluded from aggregation. On the other side, the new attacking papers, they changed their strategy to launch new attacks. So they poisoned the global model by solving an optimization problem where they craft malicious updates that they want to reduce the accuracy of the global model while keeping the updates in the safe zone. This intuition of poisoning attacks brings us to design Federated Rank Learning, or FRL. So the intuition behind the FRL is making the space of accepted updates sparser, so adversaries' choices are reduced. For example, in this figure on the left, we have current FL frameworks where the space of possible updates is continuous, meaning that the clients, they are submitting weight parameters. Each one is represented using 32 64 bits float numbers. On the right, we want a space of possible updates that is discrete, where the clients are exchanging rankings, that each ranking is a permutation of integers from 1 to d, where d is the size of the network. In FRL, instead of the weight training, we ask the clients to rank the edges in a random neural network. So the weights are kept fixed as their initial random values. What enables us to design FRL is a new concept called supermasks training. In this approach, instead of training weights, we can find a subnetwork in a randomly initialized neural network that achieves good performance. So a supermask is a mask of zeros and ones that is superimposed on a random neural network to obtain that subnetwork. For example, in this figure, on the left, we have a network of 5 nodes, 6 edges, that each edge is a weight parameter. And on the right, we want to find a subnetwork with 50% of the original network size that contains edge 1, 3, and 5. Recent line of work, they improved the supermask training algorithms, and edge pop-up is one of them. We use edge pop-up as the supermask training algorithm in FRL. In this algorithm, it assigns a score to each edge in the network, trains on the training data, and find the best edges to minimize the loss. If adding an edge to a subnetwork increases the loss, the algorithm reduces its score. Now I will explain the steps that we have in one round of FRL. So first, at the beginning, the FRL server initializes random neural network weights and broadcasts its seed to all of the clients. It also generates random scores by a seed and gives that seed to all of the clients so they can reconstruct the random scores on their side too. So note that in FRL, the weights and the scores remain fixed, and clients and server are only exchanging rankings. Another job of the FRL server is broadcasting the global ranking in each round. For example, here on the right, the server generates 6 random weights, 6 random scores, and it also broadcasts the global ranking for the first round, which shows that importance of the edges, which is 1, 2, 3, 2, 4, 5 for these scores. So in each round of the FRL, the clients receive the global ranking, and they reorder the scores based on the global ranking. For example, in this round, the clients receive this global ranking 2, 3, 0, 5, 1, and 4, meaning that edge 2 should get the lowest score, which is 0.4, and edge 4 should get the highest score, which is 1.2. After reordering based on the global rankings, each client uses edge pop-up algorithm to train the scores on their local data. And after the supermask training is finished, they rank the edges from least to most important based on the trained scores. For example, in this figure, we asked the clients to find a subnetwork of 50% of the original network. So client 1 finds that edge 4 is the least important, and edge 1 is the most important. Client 2 and client 3 also find their rankings based on their local training data. Now they submit their local rankings to the FRL server for aggregation. After that FRL server receives all of the local rankings, it applies a majority vote on the local rankings to produce the global ranking for the next round. We use border count aggregation to aggregate the local rankings. So in this algorithm, to aggregate the local rankings, the server, it assigns a reputation to each vote, sums the reputations, then sort them to find the global ranking for the next round. For example, for this scenario, the first edge got a reputation of 1 from client 1, another 1 from client 2, and a 0 from client 3. So in total, it has a reputation of 2. Now we can sort all of these sum reputations and find the global ranking for the next round. Now that I've talked about the FRL design, I'm going to talk about some results. The first feature that FRL presents is improving robustness as the adversaries' choices are reduced. In our experiments, we consider multiple data sets with large number of clients. We also compare with the state-of-the-art Byzantine robust aggregation rules, such as trim mean, multi-chrome, sinus GD, and others. And we also consider different number of malicious clients in our experiments, like 10%, 20%, 30%. And we show that FRL is substantially more robust to poisoning attacks than the state-of-the-art robust aggregation rules. For example, here, for CFAR10, distributed over 1,000 clients, 100 malicious clients can only reduce the global accuracy by 6%, which is much robust compared to the other baselines. A side feature of FRL is reducing communication costs. Because in FRL, the server and clients, they are exchanging local rankings and global rankings. And so in our experiments, we compare FRL with both quantization and sparsification methods that they also try to reduce the communication cost in FL. And we can see that, for example, on CFAR10, again, distributed over 1,000 clients, FRL achieved similar performance as Fed average with a lower communication cost, like by 35% lower. In summary, core reason for susceptibility of the existing FL algorithms, we show that a core reason for susceptibility of existing FL algorithms to poisoning is the large continuous space of values in their model updates. In this work, we show that ranking-based collaborative learning can effectively mitigate the robustness issues as well as reduce the communication involved. And we designed a novel collaborative learning algorithm called Federated Rank Learning, or FRL. Now I will talk about some interesting future directions that we are considering. The first one is one potential future direction is to investigate the effect of different rank aggregation methods in FRL. So right now we are just using the simplest method, which is board account aggregation, by replacing FRL's rank aggregation at the FRL server with alternative methods such as Quicksort, footrole, and other methods. It is possible to examine their impact on the FL accuracy in highly heterogeneous data distribution where all the rankings significantly different from each other. Furthermore, the effect of different rank aggregation rules on the privacy, efficiency, and fairness can be investigated. And another potential future direction of FRL is using the ideas that we have in current FL setting, such as Scaffold, FedProx, FedNovo, and bring those ideas in FRL and apply them on the rankings. Also, the last one is that we can bring the ideas that we have in FL personalization to the rankings, to the FRL, and apply them on the rankings. For example, fine-tuning the global ranking, or mixing the global and local rankings, and other approaches to personalize the global ranking for each client. And then our code is available on GitHub, and thank you so much for listening.